Hi, Algebra 2. To start out Chapter 10, we're going to look at right angle trigonometry. It's a little bit of review from what you've done in geometry. Here we go. This is the table from your book defining what a trig function is. And just remember that these are going to be ratios that compare the lengths of two sides of a right triangle. You have in this table the definition of sine, cosine, and tangent. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. And what we mean by those is we're referring to the lengths of the triangle. So if this is our angle theta that we're referring to, the side opposite that angle is the opposite side. The side connected to that angle is the adjacent side, and then the hypotenuse is going to be your longest side of your triangle. I like this visual to show us how to calculate sine, cosine, and tangent. The abbreviations we can remember are SO, CA, TOA. SO means that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So if you can remember SOHCA, TOA, it will help you remember how to calculate these. In this example, we are going to find the sine, cosine, and tangent. Whenever I'm working with these, when I was learning these in school, I would write the SOHCA, TOA acronym every single time. I would write at the top of my paper for every quiz, every homework assignment. It would really help. So we're going to find the value of sine, and we just abbreviate it SIN. The sine of theta, that's going to be our angle, is going to be the opposite length, which is 7, over the hypotenuse length, which is 25. So sine of theta equals, I forgot my equal sign in there, 7 over 25. And we just leave it at that. We're just looking for what is the ratio of the sides compared to our angle we're looking at. Cosine is abbreviated COS. Cosine of theta is going to equal the adjacent side, which is 24, over the hypotenuse, which is 25. And then tangent of theta is going to be the opposite side, which is 7, over the adjacent side, which is 24. This table from your book is summarizing the special right triangles. When we are looking at right triangles, a 30, 60, 90 triangle and a 45, 45, 90 triangle, we call our special right triangles because we know pretty quickly what their side lengths are. In a 30, 60, 90, the one side is going to be 1, the hypotenuse is going to be 2, and then the other side length is going to be the square root of 3. And that's coming from your Pythagorean theorem. Remember, a squared plus b squared equals c squared. In the 45, 45, 90 triangle, we have side lengths of 1, 1, and square root of 2. So then when we find the sine, cosine, and tangent of our special right triangles, we're going to come up with some values that you're going to see often. One thing to note is that in these right here, where the square root of 2 is in the denominator, or I guess up here where the square root of 3 is in the denominator, remember we rationalize the denominator because we don't want radicals in the denominator. So we would multiply by square root of 2 over square root of 2, and that's how we end up with the square root of 2 over 2 right there. In this triangle, I can see that it's a 90-degree triangle. Here's 30 degrees, so I know the other side is 60, or the other angle, and I recognize this as a special right triangle. Now I'm looking at the 30-degree angle, and the sides I'm working with are the opposite and the hypotenuse in relation to that. And so thinking of SOHCA, TOA, I know I'm going to be using sine. So the sine of 30 is going to equal x over 74. Now my special right triangle, if I look back at my reference sheet, the sine of 30 was the same as just 1/2. And now I just need to get x by itself. I'm going to multiply both sides by 74. So I just have 74 times 1/2. Well, half of 74 is 37. So x, the length of side x, is going to be 37. And this again goes back to that special right triangle, 30, 60, 90 triangle. I know that the one side is going to be a length of 1, and one side is going to be the length of, the hypotenuse is the length of 2. So in this case, the hypotenuse is twice as long as the other side, 37. Here again, I notice I'm working with a special right triangle because it's a 45, 45, 90 triangle. And I remember that those side lengths were 1, 1, and the square root of 2. And I'm working with the opposite and the hypotenuse. So I'm going to use sine again. So sine of 45 is going to equal x over 20. Now I know from my table that the sine of 45 degrees is the square root of 2 over 2. And remember, we got that by rationalizing the denominator, equals x over 20. And so now I'm just going to get x by itself. I'm going to multiply both sides by 20. And this simplifies over here. So I just end up with 10 times the square root of 2 equals x. And we're going to leave that as an exact value. Don't put it into your calculator and estimate a decimal. Just leave it as an exact value. Here I labeled what I know. I know that the eye height of my biologist is 6 feet. And then I drew this line across here because I know that this length right here is going to be 6 feet. It's 180 feet to the tree, and the angle of elevation is 38.7 degrees. So I'm looking at my triangle here, my right triangle. I have an opposite side I'm working with and an adjacent side I'm working with. And so that tells me I'm going to be using the tangent function. So a tangent of 38.7 is opposite over hypotenuse. So when I get x by itself, I got x to be 144.2. So that is this height right here, 144.2. But I know for the full height of the tree, I also need to add on this 6 feet. So I know that my total height is going to be 150.2. In these types of problems, a diagram is going to be very, very important to keep all this information straight. And here it helped us remember to add on that 6 feet, the height of the biologist. To my diagram, I've added my surveyor right here and the fact that his eye level is 6 feet from the ground. And then I've just added the hill of my roller coaster just to give me an idea of what's going on. I used tangent because I knew the opposite and the adjacent, and when I solved that for x, I got 213.8, but I needed to add on the 6 feet for my surveyor's height, so the total height of the roller coaster is 219.8.